Alright, so here we are talking about the tangent curve. I'm just going to put in one section of it. One of the asymptotes was at pi over 2, negative, and one of them was at pi over 2. And there was a snake from here to there. I'm just showing you this one section, and from that we're going to determine if it is a positive or, I'm sorry, a even or an odd function. So we're going to look right in here, and we do our x negative x test. So I pick a value and I call it x. I go out x, hit this value, read the y over here. So f of x is right there. Now I'm going to go out the same amount in the opposite direction, and to reach my function I have to go down, and I read that value over here. Negative f, I'm sorry, f of negative x. So f of x and f of negative x, in this term, in terms of tangent, that's tangent of x and tangent of negative x, are not equal. So this is a lie, but to make a truth out of it, I can put a negative sign on this side or this side. I'll put it over there, it looks more balanced. And now I have another trig ID, and this is trig ID number, what is it? Do we have 18 and 19 over here? Let's see. Yes, 18 and 19. So this is number 20. This is the 20th trig ID. And this tells us that tangent is, what do you think? Even or odd? Tangent x is an odd function. It acts like an odd function. Alright, so looking at that, we will continue. And before I leave this side of the paper, I want to mention that this has a period. I think we can see it better on this one. Remember, the period is how long, how many radians before it repeats itself. So study that. I know some of my markings are clouding over some of the radian markings, but how far is it from here to here? I think you can see that's one cycle, one period before it repeats. So we went from negative pi over 2 to positive pi over 2, which is a distance of pi. So let's make a note of that. The period of y equals tan x is pi radians, or pi. Does it have an amplitude? Well, we know how sine went up and down and established an amplitude, but this doesn't have that kind of behavior. So it doesn't have an amplitude. So we will talk more about that a value, which we used as an amplitude change in the sine and cosine curve. So we're about ready for that. So let's go on to there. I'm going to show you how to graph some tangent curves that have some alterations in their equations, like we did with the sine and cosine. So suppose we have y equals some value a tangent b times x minus c plus d. These are all of the changes I can make to the tangent curve. This, as it is with the other function, is to do with a period. This has to do with left or right translations. And this is up and down. I didn't mention this as being amplitude because it's no longer amplitude, because tangent doesn't have that sort of behavior, but it does affect the graph. And what it does, it either stretches it, it's a stretch or a shrink. And I'll show you an example or two so you get an idea of what that A does. Alright, let's do a basic one. Number 1 is going to be y equals 2 tangent x. When you have y equals 2 tangent x, you'll see that 2 is corresponding to that A spot that I was talking about. And here what I'll do is I'll give you a graph. Remember, the tangent has a asymptote here and another one over here. And the normal tangent curve comes up with a little bit of a wobble and then goes like that. This too is going to stretch that out. Stretch it out. So instead of it being like this much wobble, there's going to be even far less wobble. So I'm going to come from here, across here, and see how I even, it's almost a straight line, but I do have a little bit of slant in there. So trying to show you the difference between the two. I darken this one. So this one has less of a wobble. It's straighter than the original lighter one. So you might say, well, that's pretty imprecise. It's not precise at all. So that 2 takes some of the wobble out and makes it straighter. It stretches it. So if this was a piece of elastic and we stretched it, it would look more like this. So I'm just going to see on your graphs that there is some stretching that you've done to the graph. And the only way I can see that is you put it on the original curve as well, like I've asked you to do on the other cases. So that's a stretch. But what happens if that isn't a 2? What if it is like a 1/2? This is still in that position of letter A, and if it's a whole number, you're going to stretch. But if it's a half or a fraction like that, a proper fraction, it's going to be a shrink. So let me show you what a shrink looks like. We're going to the shrink. All right, here is my asymptotes for the regular tangent curve, and the 1/2 will put in more of a wobble. Remember, the 2 stretched it. The 1/2 is going to shrink it. And what happens is, whereas, let me put in the regular, real lightly. Here's like a regular curve with a regular wobble. The one with extra wobble is going to come up steeper and then go over and have much more of a wobble. So let me darken that. This has so much wobble on it. You could sit a glass of water there. And here, you couldn't sit a glass of water there, it'd slide right off. So see what I mean when I need more wobble? There's a place here where you could sit a glass of water. Hey, you could even put some chia seeds in it. Why not? All right, so that's wobble. So again, this is very imprecise, but I'm just looking for a trend. For the 2, I'm looking for a stretch. For the 1/2, I'm looking for a shrink, and that's what I mean by those 2 terms. All right, so let's move on and look at another change. Y equals tangent of 2x. When I have y equals tangent of 2x, I have another position taken up. And if I look back at my original key, that's my B. Notice I didn't put a formula or a key here. This has to do with period. But I think it's wiser to find the actual period of tangent of 2x by graphing the very close and helpful cousin. Remember, we have tangent is sine over cosine. So I'm going to look at cosine of 2x. And we know how that works because we just did quite a few graphs of those. And when we had the number there, we called that our b, and we said it was 2 pi divided by the period. So I'm just going to graph cosine of 2x and show you how to go from that to tangent of 2x. So our b is 2 from the formula, from the problem. Multiply both sides by p, divide by 2, and I get period of pi. So if I'm going to do a cosine curve, remember I'm graphing this one first. The cosine curve goes up, starts up at 1 and goes bottoms out, but we're going to finish that in pi radians. So we're going to have to squish it up. So here's 1, like that. And I'll put 1 on the other side. Here's pi over 2. Here's pi. So this has to come down rather sharply and go like that. So if I'm going to graph tangent from that, anywhere this crosses the x-axis, that's supposed to be right in between these two tick marks. It looks a little off. So this comes down right in the middle here. So this is like pi over 4. So anywhere the cosine curve crosses the x-axis, there's going to be a asymptote below it in the tangent curve. So here's another one, and here's another one. So I just kind of line them up. So wherever this one zeroes out on the x-axis, this has an asymptote. And that's at pi over 4 and minus pi over 4. So now I can draw in my snake. It doesn't have a number here to shrink or stretch it, so I'll just draw it with its regular bent. All right. Our time's about up for tonight, and I didn't quite finish this lesson, so what I'll probably do is take about 10 minutes of our class time. I don't want to take any more of your weekend and my video time. And so for now, bring those thoughts with us. We made some progress, but we're not quite there. So I will complete that on I'll complete that on Monday. Looks like we're not going to get stormed out. So see you then. Have a good weekend. Bye.